Good evening, folks. My name is Mark Razzie from JPL's Office of Communications and Education, and it is my absolute pleasure to be your host for this evening's edition of the Von Karman Lecture Series. Before we get started, though, let me please welcome in our co-host this evening, Sarah Marcotte from the Mars Public Engagement Team. Hi, Sarah.
Hello. Sarah Marcotte here, Public Engagement Specialist from the Mars Exploration Program. So, near the end of our show tonight, I will be fielding your questions from LinkedIn, YouTube, and Facebook. Now, if you're on one of those platforms and you don't see a chat box there, try refreshing your browser and it should pop up. Now, since you have joined us tonight and you are interested in the InSight mission's insights about Mars, after tonight's program, you might also want to check out the Science Highlights page on the mission website. So I'm really looking forward to tonight's conversation. So I will turn it back to you, Mark.
Thank you very much, Sarah. So our topic tonight, as Sarah so kindly mentioned, is in fact the InSight mission to Mars. Now, this mission planned yet another risky landing attempt on Mars and sought to reveal the interior structure of the red planet. Having accomplished that landing in November 26th of 2018, the mission went on to more than double its lifespan and finally ended in December of 2022. So to tell us more about the spacecraft and its accomplishments, we have two fantastic guests tonight. JPL's very own Dr. Mark Panning, who is the InSight Mission Project Scientist, and Dr. Ingrid Daubar, an assistant professor of research at Brown University and an InSight mission participating scientist. So to start us off this evening, let's first welcome in Dr. Panning. So, hey, Mark, how you doing, my friend? Thanks for joining us tonight.
Hi. Yeah, it's really great to be here. I'm excited to talk about the mission.
we're grateful for your participation tonight, seriously. So first, to start us all off, let's talk about the mission goals. What kind of information was InSight after?
Yeah, so so there's InSight is an interesting Mars mission in a lot of ways. So there's been a lot of missions to Mars, and most of them have been mainly focused on looking at things on the surface or in the atmosphere. And there's lots of exciting stuff to look at there. But InSight was the first mission that really the whole point was to try to look at the interior and try to understand what was happening deep inside and to use that to basically understand a whole lot more about how rocky planets are form and evolve. So that would include Earth and Venus and Mercury and Mars and pretty much the moon too. It's not technically a planet, but I will freely admit that I am loose in my definition of planet. I don't necessarily agree with the IAU on that. If we bring up image one, I think it's probably a good way of describing what I'm talking about. So when you Google what's the inside of a planet look like or something like that, you get all of these cross sections, planets cut in half, and you see all the circles that are the layers, the core, the mantle, the crust. And the kind of dirty secret is, for most of these, we're kind of guessing. We know things about the gravity, and that can give you some guesses on the general makeup of things, the general layers. But a lot of the details are missing. So you could see this is an older image from 2014 showing all these cutaway pictures. And Earth and the Moon are actually pretty well known because we've done seismology on them and we know what the insides look like. We have all of these layers pretty well known. But at the time of this figure, really all of those numbers on Mars were question marks. We just didn't really know. They were basically just guesses. And in order to really understand the interior, we decided to send a mission that was focused on doing measurements that were sensitive to the inside of Mars. So if you go to image 2, that's got a lot of the instruments that we decided to fly, and these are the three main sets of instruments. So there's the one that's out front, looks like a kind of upside down pie plate on top of it. That's the seismometer. I'm a seismologist, so that's my favorite instrument, but they're all really important. And then the other two prime instruments we had were the HP cubed, which stands for Heat Flow and Physical Properties Probe. and it was designed to go down in the ground about 3 to 5 meters, which is up to about 15 feet. And It didn't make it that far, but its goal was to be able to measure heat flow. Instead, it managed to measure some of the physical properties of the subsurface near InSight. And finally, the last major instrument, prime instrument, was the RISE mission, which basically was radio science. It was using transmitters that talked directly to Earth, and it used those in order to look at very small wobbles of the planet as it was rotating. So it's kind of, you could tell what the inside of a milk jug is when you wiggle it. The RISE instrument is to measure that. Excuse me. But it turns out all of these instruments are really sensitive. Oh, go ahead.
Yeah, no, I was going to say that's a pretty cool instrument package. And as you were going to talk about, we talked about this in our discussions beforehand. Yeah, we always tell folks, space is hard. And I remember hearing the story about when they were testing the seismometer. I think it was in Denver, that they were able to measure or actually detect like ocean waves crashing on the Pacific coast. So like, how do you guys like manage that challenge? And I'm sure that was just one of many.
Yeah, so seismometers are really sensitive instruments. It turns out if you put a seismometer anywhere on Earth, you'll always hear the oceans. It doesn't matter where you are. You can always hear the oceans if you've got a good enough seismometer. They're always making noise on Earth. Yeah, these are very sensitive instruments, and they're actually sensitive to lots of things, not just the ground motion. It turns out when magnetic storms come through, they move the instrument. When pressure and wind, all of these things affect it. So we have a secondary science payload. So that's image 3. And I'm not going to go through all of these, but this is basically a whole bunch of other instruments that are out there to measure all of the things that can complicate the measurement, particularly for the seismometer. We've got wind sensors, we've got pressure sensors, got cameras, magnetometer. All of these things actually have been able to do great science on their own. But the justification for including them was that we wanted to make sure that we were knowing all the things that can mess up the seismic signals. But what I was talking about the oceans is actually really fascinating thing to think about, because on Earth, when you're trying to get a really, really quiet seismic station, you do all sorts of crazy things. You put it deep down in mines, or drill down hundreds of meters into the ground and try to get them really, really quiet. On InSight, we flew and had an arm that put it out there on a tripod on top of a big pile of dirt, effectively, which on Earth that would make a really noisy station. But because there's no oceans on Mars, our station is about 2 orders of magnitude quieter than any station on Earth. So we installed the best seismic station in the solar system. So I'm pretty excited about that.
That's pretty impressive. So I guess once all was said and done, what were your kind of impressions of the mission? How did it do?
We did everything we promised. Basically, we were very, very, very happy with our results on looking at the interior. So if you bring up slide 4, I find this one fascinating, because this is basically all of the seismic data of the entire mission in one picture. And I think that's kind of impressive to figure out. But basically, each line going across here is one sol on Mars, and a sol on Mars is what we call a day. There, it's a little bit longer than an Earth day, but pretty close to the length of an Earth day. And the colors on each row, if it's a purpley color, it means it's really quiet. There's not a lot of seismic background noise. And if it's an orangey yellowy color, it means it's pretty noisy. And you can see the pattern every day, that it's noisier in the middle of the day and quieter at night. And you can see there's also all of these little colored dots on there. Actually, that's 1,300 marsquakes. We had a huge number that we were able to record, and you can see they happen in the purple times, because that's when it's really quiet on Mars. And so we can see these events, most of which are pretty tiny. A few of them are relatively big. You can see there's labeled there on the kind of lower left. There's one that's a magnitude 4.7. That's big for Mars. It's the biggest one we ever recorded. If you live in California like I do, 4.7 doesn't sound giant, but for Mars, that's a really giant event. So with all of these Marsquakes, we are able to look for signals that interacted with all of those layers I showed earlier. So we were able to see seismic waves that did things like bounce off the core of Mars, or that interacted with the crust below the station. And by using all of that data, we were able to put a lot of numbers on all of those cross sections, and we learned some really interesting things. For example, the core of Mars is right at the biggest end of what we expected before the mission. It's also liquid. We found that out. That was expected, but we confirmed it with the data. By the fact that it's big also means it's not very dense, which means that there's all sorts of other elements in there. So there's a lot of really exciting things, and we're very happy with all of the things we found. One of the parts we were a little concerned about, though, is that at the end of the first 2 years of the mission, which was the prime mission length, we'd recorded a lot of these Marsquakes. It's about halfway down that figure. There is where the prime mission ended. You can see there's the white dashed line there. We'd not seen a lot of Marsquakes, and we'd done a lot of the results we wanted to get, and we were pretty happy about it. But if you bring up image 5, this is a map of all the quakes that we found, and it's kind of a funny looking map because all the quakes are marked with these kind of weird black circle ellipse things. But that's how uncertain we are about the locations. It shows a lot of different things, but that's how well we can locate it, because we're just with one station, and so it's a difficult process, but we're able to locate all of these events. But at the end of the mission, we weren't sure we'd seen any impacts, and that was one of our goals. We wanted to see not just Marsquakes, we wanted to see impacts from space. It turns out Mars was waiting to give us things. We got through the prime mission, and we didn't see anything that we were convinced of, but the good stuff was coming, and there's some colored symbols on there that our next speaker is going to talk about in a lot more detail. But that was one thing we were worried about at the end of the prime mission. But Mars really helped us out when we extended for another full Mars year, which is about 2 Earth years, to get quite a bit more data.
Nice. That's cool. That's a really vast data set. So let's dive into that then. So to do that, I'd like to bring back in Dr. Daubar, who I mentioned before is an participating scientist on the InSight mission. Ingrid, thank you so much for joining us tonight, folks. I want you to realize she's joining us from the East Coast, so it's a little late, but we're grateful for you. For playing with us tonight. So first, let's talk about the kind of data you were expecting to find. Thanks.
Yeah, so if we bring up the next image, this is an artist rendition of what we thought we would see with InSight. Before InSight landed on Mars, we thought we would see kind of a steady stream of impacts. And this is when a meteoroid, a piece of a comet or an asteroid, hurtles through the Martian atmosphere and hits the surface, creates a crater, and the seismometer pictured here would be able to kind of sense that ground shaking. And one thing that impacts have going for them that regular quakes don't is that we can tell exactly where they happened. So we saw in Mark's map where they had these funny loopy circles. But if an impact happened, we could try to image it from orbit, and then we would know exactly where it happened. Unfortunately, for the first 3 years on Mars, all we had was this artist rendition, and we didn't find anything that we thought was an impact.
Oh no. 3 years. That's a while for it to be that quiet. Did the data finally start rolling in at some point? I guess after that, yes.
Yeah, so we finally detected the first impact seismically, and I think if we go to the next image, this is a seismograph. Instead of the kind of normal wiggles that you might see, this shows the power in different frequencies over time. So this was the one event that we finally recognized as an impact after all.
Oh, looks like we might have lost Ingrid there for a moment. So, yeah, this chart, as we had this discussion a little bit earlier, this shows you some of the acoustic waves that the spacecraft recorded as it impacted the surface. I think the next slide will actually show us, you'll be able to hear what this sounded like. If we could roll that.
Yeah, so I'm glad you're listening to that while I dropped off there. I love that sound. Um, it's actually my ringtone.
I love it.
So, yeah.
Very cool. Yes, I just talked a teeny bit about it just to fill in. If you want to talk a little more
Great,
to it, feel
great.
free.
Yeah, so this is if you take that seismograph and you translate it to frequencies that the human ear can hear, this is what it sounds like to have an impact on Mars. So we were super excited when we finally heard this. So if you go to the next image,
That.
we actually found a couple of these. So this is a map that shows 3 of these impacts that occurred right near the InSight lander. And because once we got these bloops, these chirps in the seismic data, we could get an estimate of the location of the impact, and then we could ask our friends over in the Mars Reconnaissance Orbiter to take an image with the orbiting cameras. So these are context images and high-res images, and it shows a before and an after that shows the new crater has formed at the same time as we got that seismic data. And then we have a couple of close-ups of these in the next few images. Yeah, so
Let's see
these
some
are
of
just
those
really
highlights.
gorgeous high resolution images from the high-res camera. And go to the next one.
Cool.
These are enhanced false color. So the kind of blast zone around the crater is much bigger than the crater itself, and it shows where the dust has been disturbed by that impact. And these craters are really tiny, actually, in terms of the rest of Mars, the rest of the craters on Mars. These are only a few meters across, maybe 10 meters at most. But even though they were tiny, they were mighty, and they were nice and nearby InSight, so they gave us some really good seismic data.
So I know we wanted to go back and visit one of the images. Which one was it? Was it 12, or is that what we're showing now?
Yeah, so
Nope, did we lose her again? Oh, there you are.
image 12. Hopefully I'm still here. Image 12. So this is the big one. This is the really exciting one. After we had found those small ones near InSight, we thought that was super exciting. And then this happened. So this happened on Christmas Eve of 2021. And it's the biggest crater we've ever seen form. So this is zoomed way out. This is a context camera image from orbit. This whole blast zone around the impact is about 30 kilometers across. And we can zoom in with video 14. And this is a movie made from a 3-dimensional image from the high-res camera. And what we're doing is we're flying over this crater that formed. So it's a huge crater in terms of current cratering. It's about 500 feet across, or about a city block across. And you can see there's these white splotches all around it. This crater actually coincidentally happened at 35 degrees north latitude, right at the edge of where water ice is stable in the shallow subsurface. So when this crater formed, it excavated these chunks of ice. You can see splashes of ice out in the ejecta, and some actual chunks of ice that were thrown out when it occurred. So this particular impact was super exciting. These things, we would expect this size crater to happen only maybe once a generation, once every 20 or 30 years. So the fact that it happened while InSight was listening was just a huge coincidence and very fortuitous. So because it happened on Christmas Eve, this really was a spectacular gift for impact science.
That's super cool. Love that. That video is great. So, even though the mission has kind of officially ended, right? I have to imagine there's still a ton of data that you are still continuing to sort through.
Yeah. So we, if you go back to the map that Mark showed, image 5, so that shows just some of the quakes that that are those among those 1,300 quakes. And now that we have these impacts that we just learned about in the last year or so, we have a lot more still to do. So people are going to be studying this for a long time.
Very, very cool. All right. So, given that, I think it's probably a fair time to start checking in to see what kind of questions we might have. So, Sarah, if you're out there, how's it looking out there in the social world?
In the social world. So the questions are coming in, and they are very interesting questions. So I can dive in to a couple of them right now. So allow me to read on my screen. So I thought this was a nice sort of overarching question. So this is from Dan on YouTube. Dan asks, so what is causing the quakes? There's no tectonic activity, is there? Is it cooling of the crust?
Yeah, that's a really, really good question, and one we thought about a lot going in. So there are tectonics on Mars, but there are not plate tectonics on Mars. So if you took an intro geology course somewhere in your career, you probably learned about plate tectonics, which is what governs most of the earthquakes and volcanoes on Earth. The Earth is divided up in these plates, and they rub against each other, and that's where quakes happen. Mars doesn't show any evidence of plate tectonics. But on Earth, we actually do see quakes in between those plates as well. The stresses build up, and you see quakes happen. On Mars, there's probably lots of different things causing it. Going in, we thought overall that the planet cooling and contracting would be the driving force of most of the quakes we saw. Now we're not sure exactly whether that's the driving energy for most of them or not. It turns out, if you look at that map number 5, that there's this whole big clump of circles there to the east of InSight. There's a whole bunch one right there. That's an area called Cerberus Fossae. And it's actually an area that shows the youngest volcanism on the surface of Mars. There's eruptions within the last 10 million years. Now, that sounds like a long time, but geologically speaking, trust me, that's young. And so it seems like actually a lot of the events we're seeing are related to ongoing volcanic activity, at least in this location. There's probably lots of other things that can drive Mars quakes as well, just gravitational settling of these big loads. There are giant volcanoes on Mars. Olympus Mons is giant, and it's sitting on top of the Tharsis Bulge, which is even bigger. It's a big weight sitting on top of the planet. You get gravitational stresses because of that. There's likely other things that we haven't thought of yet, but there are things that cause stresses which can cause quakes, even if there isn't plate tectonics to drive the level of earthquakes that we see on Earth.
Okay, so I have kind of a related question to that. So I'll stay with you, Mark, and then Ingrid, I have a really good, juicy, I can't decide between two for you next. Okay, so Bruce on YouTube asks, is there a minimum size of a planetary body for plate tectonics to take place?
I don't know if there's a minimum size. There's whether plate tectonics happens or not is one of the things that drives why we want to do planetary seismology, planetary science in general. If it were just size that drove plate tectonics, we would expect to see evidence of a lot of plate tectonics on Venus. Venus is almost exactly the same size as Earth, and yet it shows no evidence of anything like plate tectonics. So there's obviously a multiple set of ingredients that go into whether we get plate tectonics or not. And I'm not going to give you a glib, I know the answer here, because I don't know the answer. People think it may have to do with presence or absence of water in the Earth's mantle. There are lots of people who have lots of theories, but this is why we study other planets. Actually, this is something always came up before the mission. People are like, well, why are you going to, put a seismometer on Mars? It's a lot of effort. It's a long way away. I say we want to study these other planets because it's like you don't become a really good doctor by only working on one patient. So if you want to understand planets, you got to work on multiple patients here. And so this is one thing we're looking at and trying to understand this better.
Okay, thank you. So a lot of impact questions are coming in, Ingrid. So we might keep you here till, midnight, but I'll just pick and choose some of the good ones. They're all good. I love all my children, but there's some very interesting questions here. So where was it? I've already lost it. There it goes. Manny on LinkedIn is asking, are any of the impact sites being investigated for new material elements?
So I'm not sure exactly what new material elements might mean, but the one that we showed the video of, it does have exposed water ice, which is really exciting to see because it's the closest to the equator we've ever seen water ice. So that's telling us a lot about kind of the climate history of Mars and when the water would have been stable there, and also what resources might be close to the surface for future exploration.
Neat. Well, then you answered the question from Ankit on Facebook because Ankit was wondering if the crater's data analysis was showing any signs of water. So it sounds like water ice is evident in at least some of the craters.
Yeah, those bright blotches that you saw in the video, that's all water ice. Mm-hmm.
Neat. Okay, so I have to have another impact question. So Lily Flower on YouTube is asking, so how small are the rocks that cause all the craters and how fast are they going when they hit?
Oh, that's a really good question. So we are able to make some educated guesses about that. Usually they're about 10 times smaller than the crater itself. So for this 150-meter crater, it was probably 15 meters in diameter, roughly. Of course, the impactor is completely destroyed, so we don't actually have any evidence of it. But we can do that based on modeling and what we know about impact physics. And in terms of how fast they're going, most things hitting Mars are going about 10 kilometers per second, but the atmosphere, even though Mars has a very thin atmosphere, it's still substantial. It's enough to slow down these impactors. So we think the really small ones, like those really small craters that I showed, those impactors get slowed down to something more like a couple kilometers per second. But that's still really, really fast enough to cause a big explosion, make a crater.
Okay, this one is for you, Mark. So, and you alluded to this a little bit earlier. So, Siam on LinkedIn is asking, will the data be publicly available too?
So the seismic data not only will be publicly available, it is already publicly available. We basically throughout the course of the mission released a chunk of data every 3 months. This was one of the selling points of the mission from the beginning, is that we wanted to be very open and let all seismologists who wanted to look at the seismic data do it. People who wanted to get access to the weather data came out even faster. That was out on the web basically as soon as it came down. You could go and look at what the weather was like at the InSight landing site anytime you wanted. But all of the seismic data from the mission is available. It's through multiple websites. If you're a seismologist, you may know about IRIS, which is the Incorporated Research Institutions of Seismology. You can download our data there just like you would download any other station on Earth. It's just on Mars. So that data is available, and we love to see other people work on the data. I have high expectations that people will be working on this data for a long time to come. The only other extensive data set of planetary seismology, and I'm being loose on planet, but the Apollo landings all included seismometers, and 4 of those landing sites had seismic stations that lasted a long time. They actually got turned off in 1977, 2 months after I was born, and people are still publishing. And while I'm still only 21, Maybe that was a little bit longer than that ago. People are still publishing with that data, so I'm expecting that some of the newborns today are going to be publishing about InSight seismology when they're grizzled old seismologists.
Great. Okay, I have probably for you, Mark, as well. These are two questions from YouTube, but they're kind of related. And there's so much enthusiasm out here. So Tim on YouTube is, ooh, I hope we see more seismometers on Mars. So what's next? Any plans? And then Riddle on YouTube also is asking, what about Venus? Can we put a seismometer on Venus?
These are both great questions. I will say for Mars right now, there are no direct plans. There are no plans specifically in the works to put another seismometer on Mars. I am optimistic that there will be more seismometers on Mars in the future, but that's subject to the people who hold the purse strings. But for example, I would love to see landing a small network of lower sensitivity seismometers, but are landing right on Cerberus Fossae. I think that'd be great. I think we could do some really cool science there. But we have to be patient. Planetary science is really all about patience. Missions take a long time to develop. And so we started the process. Well, if you talk to the principal investigator of InSight, Bruce Bannert, he basically began work on trying to get seismometers on Mars. Certainly back in the 90s, perhaps back in the 80s. And it's been a long process to get to the point that we got data from Mars in 2018. So certain amount of patience on that. As far as other planetary bodies, I will say we already have data from the moon, but there will be more data from the moon. I'm personally involved in getting a project where we're trying to land a seismometer on the far side of the moon, which is going on a commercial lander. As far as Venus, landing a seismometer on the surface of Venus, I think it would be great, and I would love to see it, but there's some really big challenges with that. You want to have a long-lived seismic station on a planet that's very, very hot, very, very high pressure, in a very, very corrosive atmosphere. That's a challenging mission. People are working on developing electronics and seismometers that may be able to work in that condition. But I would imagine what we'll see before then, and what I hope to see, is to see balloons going in the atmosphere of Venus. And you can put pressure sensors on those. And it turns out seismic waves do couple into the atmosphere. On Earth, you can see earthquakes by bouncing signals off of the ionosphere. Similar things could be done in the atmosphere of Venus. So there are people who are working on that all over the world. Some people here at JPL are working on that, thinking about ways of doing seismology on Venus.
Wow. So, Mark, I see you've put some thought into this. That's good. Should always have a few
kind
proposals
of my job.
in your pocket, just in case, you might meet someone in an elevator, whatever. Okay. Ingrid, this question is for you. This is from Henry on YouTube. Henry is asking, how do you differentiate the quakes caused by the foreign impacts as opposed to the ones created by the Mars tectonics?
Yeah, that is such a good question. And before we got to Mars, we had all kinds of ideas on how we might tell the difference between quakes and impacts. Most of those were wrong because that's what happens when you do exploration. And those the bloops that you heard, the little chirps, those are the main things that that we use to differentiate impacts from kind of internal tectonic sources. It also helps when we have an image of the crater. So in the case of the Christmas Eve crater, we actually had the image of the crater first, and then they connected it with the seismic signal. So there are characteristics of the seismic signals that can tell us that they are quakes. That we're learning because Mars is teaching us new things even as we go.
Okay, so Mark, may I ask another one? I think we're still going okay. All right, so this is from Jared in YouTube, and Ingrid, I'm going to keep it with you here. Did we learn anything about the frequency of asteroid impacts on Mars, and were there fewer than expected?
Yeah, so that's something I'm trying to I'm working on actively right now. Um, there weren't necessarily fewer than we expected. Um, Insight can only detect things if they're really close or really big. And you can see that's kind of the ones that we saw were the small ones were close by and the big ones were far away. So if you look at it kind of overall, it's about the rate that we would have expected, but there is kind of a coincidence in timing where we didn't see anything for the first 3 years, and then we saw all of them kind of towards the end of the mission. So it's still kind of an open question, I think, whether that's just a coincidence or we just got lucky, um, or whether that's just Mars having fun with us.
Mars is always having fun with us. Apparently, Mars observes certain holidays too, um, and sends asteroids your way to fit in your Christmas stocking, I guess. Um, I have another question. Actually, I'm going to throw this one at you, Mark. Not throw it at you, but you know what I mean. Chris on LinkedIn is asking, why were you not able to reach the 15-meter depth target? I assume he's talking about the HP cubed instrument.
Yes, and that's a really good question. So the HP cubed mole, which is what we called the part that was supposed to go down, effectively is what you could call a self-driving nail. It's this long cylindrical thing, and it has a mass in it that gets cranked up and then drops down. And that hammers it down a little bit, and then it just repeats that over and over again, and is designed to go down. And on tests, it could go down in loose material at quite a distance. What our leading understanding for why it wasn't able to penetrate as well as we had expected is that the surface material where we landed ended up being a little more cohesive. It stuck together better than we had modeled beforehand. And so as the mole was going down, it actually pushed the material away and made a pit around the mole. And we actually saw this. We picked up the structure that had been sitting on top of the mole and moved it aside so we could take pictures of where it was, and it opened up a pit around itself. And so when that happens, the hammering happens and it goes down a little bit, but there's no ground around it to resist it just popping right back up. And so it wasn't able to penetrate. In fact, at one point in the process of trying to get it to go down, it actually backed itself out. Actually, 2 points it backed itself out. It was a lot of stress. It was so we did lots of things to try to counteract this. We dug in material, filled in around it, and pressed down. And with a lot of work, we were able to rest the scoop on it. And which this was a really fun job for all the engineers, coming up with things to use the scoop for. At some point in the mission, we had considered not including the scoop because we didn't have plans for it, but we managed to use it for all sorts of different things. But with that, we were able to push it down, and we buried it and pushed down on it. But even with that, it still just kept opening up pits around itself, is all we can figure, and was just never able to get down as far as we wanted to go. But it did get entirely buried, and so it was able to make some measurements of the properties of the near surface of Mars, which are very interesting, and there are still coming science papers looking at all of that in more detail.
I like it. More papers, more fun. I have another question from Jared on YouTube asking, and I guess I'll stay with you, Mark. How much did the results of the seismometer compare with the previous estimates of the Mars interior?
Yeah, there were no things we found that our pre-mission expectations were totally wrong. So but there were things that, so we had broad uncertainty on how big things were. So, example, the radius of the core, the range of estimates of the size of Mars core before the mission were about 300 or 400 kilometers of variability. You could either have a really small dense core, or you could have a really big not very dense core. And so when we got the data, we found out it was a very big, not very dense core, and it was right at the upper end of that limit. The crust was kind of in the middle of the range. There had been some papers that had come out that had made big splashes that said Mars was going to have a very thick, very dense crust. And as soon as we started seeing details on the thickness of the crust, we knew that we could eliminate those models. That it didn't have that, and so it was more about going from what the pre-mission expectations were, which had very large uncertainties, and discovering that those pre-mission expectations weren't wrong, but now we are able to really narrow in and say the real size, and start getting at, what's in the core. For example, for it to be that light, there has to be a lot of stuff besides iron and nickel, which is most of what the core is made out of. And so I think there's going to be lots more thinking about the interpretation of all of that and what it means for, why Mars doesn't have a magnetic field, an internal magnetic field now. There are lots of questions that we can start addressing now that we understand how big the core is, and a little bit more about its chemistry.
Excellent. Okay.
Very good.
Thank you,
Mark. Sarah, let's do one more, see if we've got anything we can throw to Ingrid's way.
Yeah, I've got one for Ingrid right here. I have it right in my pocket. This is from Dan on YouTube, and Dan's going to bring it home. Dan asks, do the moons, Phobos and Deimos, have any effect on the trajectory of the meteors?
Oh, that's a really interesting idea. I think they would probably be too small to really affect them too much. Phobos and Deimos are pretty small as moons go, and the things kind of coming in to hit Mars are coming from all directions. So I suppose once in a while they probably do intersect them, because we do see craters on Phobos and Deimos. But in general, they don't have enough gravity to really mess with everything that's coming to hit Mars.
Very good. Well, everybody, I think we're going to wrap it up. Thank you so much for everything. That's all the time we really do have. So first of all, let me thank Mark and Ingrid for all your time and dedication to this mission. Sarah, thank you so much for handling all those questions, and all of you folks on social media behind the scenes that helped make that happen. Our audiovisual team for making this work, of course. We really appreciate all of you. And of course, everybody watching tonight. Thank you so much. This is your space program after all. It's the least we can do is to present these things for you folks, to kind of keep you up to date and let you know what's going on. So we really appreciate your interest and enthusiasm. So please join us next month when we'll talk about the amazing cryo cooler that's on the James Webb Space Telescope, which is one of the things that really allows it to peer into the deepest parts of our universe. That'll be a really neat talk. So until then, stay safe, stay curious. Good night, everybody.